Welcome everyone to the Moses Lake Museum and Art Center's Spring Lecture Series. We're happy that you're all here this evening. I just want to let you know that we're recording this session, so we ask that you hold your questions until the end. Mike Brady is a retired senior associate professor in biology from Columbia Basin College in Pasco. He graduated from Central Washington University in 1981 with a master's in biology. When he retired from the Army in 1996, he began teaching biology in North Carolina before moving back to the Pacific Northwest. Mike got involved with the Moore Observatory on the Columbia Basin College campus and reignited his passion for astronomy and astrophotography. This led him to dive into his hobby by purchasing his first telescope and mount, sparking a deep fascination with astrophotography. He and his wife Priscilla live in Moses Lake. Please help me welcome Mike Brady. Thank you, Mike.
Thank you. So like usual, we're experiencing technical difficulties there at first because I was supposed to have a mic on my shirt, but we won't have that, so we'll just go with the mic up here. Is this loud enough for everybody? Nope. Okay. I was worried about that too. So, hello. It was working. It's just probably not loud enough. I don't want to have to put my face right on top of it. Which one is it? Is this better? Is that better? A little bit louder, maybe. How's that? That good? Okay. Well, she already did a pretty good introduction. I was going to go through some more detail about my background on this first slide here. So as Tamara mentioned, I graduated from Big Bend Community College right here in Moses Lake in 1973. I'd already pretty well firmly established what I was going to do with my college career, which was to study reptiles. So after I finished with Big Bend Community College, I transferred to Central Washington University, primarily because Dr. Philip C. Dumas was my major professor there, who had a strong background in herpetology, which is the study of reptiles. And so for the next probably about 10 or 15 years, I was in my reptile phase. I was totally committed to studying reptiles, in particular rattlesnakes. My master's degree at Central Washington University was a demographic study of the rattlesnake, the western rattlesnake. And then not too long after I finished my master's degree, I joined the Army in 1981, and I was in the Army until 1996, in which I was able to take an early retirement. At that time, they were going through a downsizing, and so they offered an early retirement for 15 years, and so I did that. And I retired out of Fort Bragg in North Carolina, and since Fayetteville Technical Community College was right there, I decided I'd try my hand at teaching biology. And so I did for the next 10 years, was teach biology at Fayetteville Tech Community College. And that's where I met my wife too, Priscilla. She joined me there, and she actually joined me in scuba diving. So then I was in my next phase, which I went into that full-heartedly, and really got into scuba diving and became an instructor. So I taught scuba diving for about 20 years. And then we decided that we wanted to move back to the Northwest. I'm originally from Montana. That's where I grew up. Moved here when I was in high school and college. And so we moved back, and I ended up getting another job at a community college at CBC in Pasco. And that's where I ran into the observatory at CBC. And Mike Durst at the time was the director of the observatory. He and I became very good friends. And he retired not too long after that. And when he did, he recommended me to run the observatory at CBC. So I was a director for about 3 years just before I retired. And that, as she mentioned, was what really got me going on the astronomy aspect of my life. And right there on the right, that's the CBC observatory and the 16-inch telescope there. Of course, you can't just have one telescope. And so I have quite a collection of my own telescopes, and I also have my own backyard observatory, which we'll talk about here in just a few minutes. And one of the things I wanted to do was to kind of give a history of astronomy and photography, which kind of leads me to what I've done as far as my astrophotography goes too. When I was at Central Washington University, I took a lot of photography classes too. In fact, I basically majored in photography. And I don't know if anybody even remembers. Well, some of you, I'm sure, remember film. Although it's really hard to find film canisters anymore, and it's really tough to find a film camera since we've gone digital. But because of that, because of going into the digital age, us amateurs are able to produce some very nice photography of the night sky, and that's one of the things I wanted to kind of talk about tonight. So everything, because it's digital, is easily manipulated with software and computer programs, and that allows us to be able to really get some nice photographs. Of course, everybody has cameras now. Cell phones have just flooded the world, and now we've got cameras everywhere, and everybody's becoming a photographer. But one of the nice things about that is it allows, again, a lot of amateurs to do good photography. And I thought I'd also talk about light. We almost have to talk about light and how light works to a certain degree in order to understand how photography works and thus how astrophotography works. So our eyes are basically a little camera. It has a lens, and the lens is, I don't remember how to operate this thing. Oh yeah. The light's not working. Well, I guess I won't use my pointer. Well, the lens, of course, just like the camera lens, it's going to focus the light. The light is focused back here to the retina. The retina is a sensor of types, just like in digital cameras. Digital cameras all have sensors of some type, and the sensors are sensitive to some form of electromagnetic energy. In this case, with our eyes, we call it visible light, which I'm going to talk about here in a second. And in the retina, as you can see in the far right-hand side, the retina is made up of a series of light receptors called cones and rods. The cones are primarily sensitive to black and white light. I'm sorry, the rods are sensitive to black and white light, and the cones are sensitive to color. So the cones, which they look like an ice cream cone, that's the red, green, and blue ones, they come in red, green, and blue. And if you are familiar with photography at all, you know that those are the primary colors. By combining red, green, and blue in all sorts of ways, you can get all the colors of the rainbow. And that's what our eyes do, is pick up all those different photons of light and convert it into something that we see as light and color. Yeah, so here's the electromagnetic spectrum. It goes all the way from gamma rays on the left here to long radio waves on the right. And you can see just that narrow band in the middle is what we see, visible light. And so what we've done is develop cameras that have the same kind of sensors in them to pick up that visible light and then convert it into what we see in pictures. And we can't really talk about astronomy or photography without talking about Edwin Hubble. Of course, he's the one that the Hubble Space Telescope was named after. He's, in astronomy, he's sort of like the Charles Darwin. Darwin with his theory of evolution, which revolutionized biology. Well, Edwin Hubble revolutionized astronomy because he came up with several things that we had no idea about until he figured it out. For instance, as you can see on this picture right over here, this is one of his pictures. Now, back then, he didn't have digital cameras. What he had was, he didn't have film. Film hadn't even been really invented yet. So what they did was they had glass plates that had an emulsion, like it says here, an emulsion of silver gelatin on it. And they placed that in front of the eyepiece or the telescope. And the light landing on that plate of glass is what would turn into a picture. Now, the other thing that he had to do was he had to manually sit in front of the telescope all night long and keep the telescope centered on whatever he was taking a picture of. These mounts that we have nowadays eliminates all that. All you have to do is say, okay, point here. It stays pointed there. It tracks it perfectly. So you can go to bed while your telescope and camera are taking pictures all night long. Next morning you get up and you've got your pictures, which we'll talk about here in a minute. So as a result of taking pictures, in fact, the Andromeda Galaxy is one of the things that he was taking pictures of a lot. And he noticed that there was a variable star in that. They didn't even know that was a galaxy at the time. They thought it was a nebula of some type within our own Milky Way galaxy. At the time, in 1923 and before, the only galaxy we knew about was our own, the Milky Way. And everything else out in the night sky we thought was just part of our own Milky Way galaxy. Well, he changed all that, because when he saw that variable star in the Andromeda Galaxy, the variable star told him the distance to that galaxy, and the distance was 2.5 million light years. Well, and immediately he knew that was not within our own galaxy. That was far, far outside of our galaxy. So now all of a sudden that just opened up the entire universe. Before that, astronomers had no idea that there was all those galaxies out there. So yeah, he's the father of everything that we know about as far as the galaxies go. The other thing that he then observed was that there was a redshift in all these galaxies in the spectrum. The redshift told him that things were moving away from us, and fairly rapidly too. So that's where we came up with the expanding universe, was because of Hubble noticing there was a redshift in the spectrum of all the galaxies around us. So a lot of things he did. All right, so let's talk about distances and light and how far these things are. So in order to understand this, we have to understand some of the terminology. And one of the things that astronomers use is light years for distance. Because if we talk about kilometers or miles, our minds can't even grasp that because it's so far. So here's an example. So here's the Andromeda Galaxy, and as he discovered, it was 2.5 million light years away. Well, what does that really mean? Well, first of all, let me ask you a question. Does anybody know how fast light travels? Anybody have any idea? Since we're basing distance on light, we have to know how fast it travels. Okay. Anybody know? There's some whispering. Well, it's 186,000 miles per second. 186,000 miles per second. So if you multiply that out over 1 year, that's 6 trillion miles, approximately, rounded up. Okay, so 6 trillion miles, that's how far light travels in 1 year. So that galaxy is 2.5 million light years away. So how do you figure out how many miles that is? You have to multiply the 6 trillion times the 2.5 million. And now you've got the zeros that go around this room a couple times. It's a long ways. So that's how distances are measured in light years. Now, just to give you an idea what million, trillion, and billion means, 1 million seconds is 12 days, approximately again. 1 billion seconds, 32 years. You can see how exponentially that increases each time you go up to the next huge number. So 1 trillion seconds is 32,000 years. That's how many seconds that is. Now think about our national debt, right? That's a lot of money, a lot of money. All right, some more terminology. One of the things that I've been taking pictures of is nebula. And there's 3 basic types. And all 3 of them are in this picture of the Trifid Nebula. The red area is the emission portion. Emission meaning that the red designates that that's hydrogen gas that's been ionized. It's now been energized. And because of this ionization, it glows red. So that's the emission part of the nebula. The reflection part is the blue area. And the blue area is basically dust and gas that's reflecting the light off that dust and gas. And it glows kind of bluish because most of that, or a lot of it, is oxygen. And then the dark areas, those dark areas in the middle of the red, those are absorption areas or dark nebula. And basically, the dust and stuff is so thick in there that it's blocking the light. So you just see darkness there. So those are 3 basic types of nebula. Some more naming. So 3 main types of galaxies. There's a few other types, but the 3 main types are spiral, elliptical, and regular. The Andromeda Galaxy is an example of a spiral. And the 2 blobs there you see, that right there is M110. The other one is M32. Those are both galaxies also, but they're called elliptical galaxies because they're just kind of an oblong, roundish shape. And then over on the right, the Whale Galaxy is an irregular galaxy. They don't have any particular shape. They're kind of oddball shaped. So those are the three basic types of galaxies. So throughout the generations of astronomers, people have been cataloging all the things that they see in the night sky. And one of the first ones that was fairly famous at this was Messier, Charles Messier from France. He's an astronomer that was alive in the 1700s. And his Messier catalog is probably the most famous catalog of things in the night sky. What's funny about it is when he was cataloging all these things, what he was looking for was comets. He wanted to be famous for finding comets. But every time he was looking for comets, he'd find these other things that were getting in his way. So he started listing them. And that's where the Messier catalog came from, was him listing all the things that he thought might be a comet, but turned out not to be, nebula and galaxies and globular clusters and other things that he has in his list. He has 110 objects now on his list that he ended up with that are called Messier objects. Since then, there's been a couple other major catalogs that have been developed to catalog and categorize all the different things in the night sky. One of them is called the New General Catalog, NGC for short, and the Index Catalog, IC for short. So when you see names of things from the night sky, it's going to be, sometimes they're in all 3 catalogs. Just depends on who names them and who discovers them. Now, when I first started in this expensive hobby, I started with a basic tripod and a camera, and most people do. That's kind of how you start to take pictures of the moon or the sun if you have the right filters and things that are fairly close and fairly easy to photograph. But if you want to really get into it, you have to start looking at telescopes and mounts and things like that. So here's my 2 mounts and a couple of my telescopes, and one of them's right here in the stage. In fact, while we're looking at it, I'll just name some of the things that are on here. So the telescope is this part right here. It's a small telescope. It's 1 millimeter, but it's one of my favorite telescopes. So there's another small one right here. This is the Didescope. talk about that in a minute. It has a guide camera. This is the main camera right here. And there's actually a focuser right here, an automatic focuser attached to that manual focuser. And then you have the mount. The mount's probably one of the most critical things as far as being able to take pictures of the night sky. Because the mount does a couple of things. First of all, it puts a nice solid base, puts your telescope and camera on. And the other thing it does is it tracks. It tracks at the same speed that the Earth is rotating, so it can stay right on the object you take a picture of. Because most of the time when I'm taking pictures, it's going to be pointing at that object all night long, 5, 6, 7 hours. And it's going to be taking individual pictures of probably 3 to 5 minutes, individual pictures that you then stack later on. But it has to stay right on that object. So it tracks, but just to make sure it tracks perfectly, you also have a guide scope and a guide camera. The guide scope is pointing at a star that you pick out. It's in the same general field that the main scope is pointing at. And it zeroes in on that star, and then it stays on that star. You can crosshair on it, and then it feeds information to the mount to make sure it stays right on that star. So you stay perfectly aligned with the night sky. It's genius what you can do now. Hubble would have killed for this. Because he could not have he would have been sitting over the mount all night long, manually keeping that telescope pointing whatever he's taking pictures of. And that's what everybody had to do until these things came along. It's awesome. My other mount, the big one right here, is like right in my backyard. This one's even better. You don't have to have a guide scope. Once you get it aligned and you do a series of pictures called, it's called a T-point model. You just start it, and it automatically goes around the night sky taking pictures, and it figures out perfectly where it is. And once you've done that, it will guide perfectly. You don't have to use a guide camera, which is also beautiful. It's great. Now, what does the mount do? Well, as I said, it tracks, but it moves in 2 different directions. Show you to illustrate that. So the telescope itself. All right, so the telescope itself can move this direction. Everybody see that? Or this direction. And back the other way. And then the mount itself can also move. So by having those 2 motions together, you can point it at anything you want to in the sky, and then it starts tracking automatically. Once you point it at something, it starts tracking. And that brings me to the next thing. So the beauty of this one is, remember the cell phone? This thing runs it. My phone with an app can run that. Does the same thing from your phone or from an iPad. And once you have everything set up within the app, you can then set up how many pictures you want to take, how long you want each picture to be, and then just say go, and it starts doing that. And you tell it you want to stop at the end, and it does. So you go to bed. In the morning, it's done. And you got all the pictures ready to stack. It's awesome. I used to have to wake up every once in a while with my old mounts and check to make sure everything was going okay. Not anymore. It's great. Things have just developed that fast in the last 15 years that we as amateurs can do all this stuff now. So what those motions are is when the telescope itself is moving like this, that's called declination. And when the mount is rotating, that's right ascension. And those 2 terms basically go right over to this slide right here that talks about altitude and azimuth. So here's a person standing on the earth, looking up at the night sky. Altitude is how far above the horizon an object is. And azimuth is how far that object is from north, east to west, or south. So those are the terms you might hear astronomers using, is altitude and azimuth, to describe exactly where in the night sky that they're looking in numbers. They have numbers that match to those. All right, so what do I have? As I said, you can't have just one telescope, right? My wife will attest to this. I've gone through a number of telescopes. The other good thing about right now, since there's so many amateurs out there, there's actually an Astromart. You can start by buying used equipment, and then you can trade it as you move up, and that's what I did. I started with fairly inexpensive and started moving up into more expensive and better telescopes and mounts. So what I have right now, in fact, I just purchased this one a couple of weeks ago, 140 millimeter refractor telescope, which we'll talk about in a second. Over here, 8-inch reflector. I'll describe what those two differences are in a second. And I have a couple other small ones. Now, why do we need different sizes? Well, it depends on what you want to take a picture of. The larger ones, like the 140 millimeter and this 8-inch, well, basically a telescope is a light bucket. You want to gather as much light as you possibly can in order to get as much detail as you possibly can. So the larger the mirror, or the larger the lens, the more light you can get in onto that camera or onto your eye to see more detail. And it's not really magnification. Magnification comes from either the eyepiece or the camera or whatever you're putting on the end of the telescope. The size of the telescope is just increasing how much light is being gathered to that camera or to your eye. And then you do the magnification at the other telescope. Okay. So here's a refractor. Refractor uses lenses. And in this particular case, there's two lenses right here in this telescope. That's an achromatic telescope. Two lenses do a little bit of correction for what's called aberration. But if you had 3 lenses or even 4 lenses, that's better. The more lenses you add, the better the picture's going to be at the end. If you only use 1 lens, you get what's called aberration. Your stars are going to have a red side and a blue side. You want to get rid of that color. You want to correct for that color, get rid of it. So by adding more lenses, it color corrects the final picture, gets rid of those aberrations. Anyway, the lens focuses the light to the eyepiece or to the camera, just like the lens in your eye. Reflector telescopes use mirrors. And this is the primary mirror is back there at the back, big mirror. And has a hole in the middle for the eyepiece or your camera. So the light comes in from this direction, hits that primary mirror, is reflected to the secondary mirror at the front, and the secondary mirror then reflects it back to your eyepiece or to your camera. Now, one of the major differences between these two telescopes is the mirror telescopes, the reflectors are cheaper. And so you can get huge, much bigger mirrors for less money. So you get a bigger light bucket for less money. The reflectors are more expensive because they're making lenses, which are harder to make. Now, there's a couple other things on the telescope I haven't talked about yet, which we're going to talk about now. And that's these red boxes right here. The Sky Fusion and the SI Air, which is this box right here. little computers. The Sky Fusion computer, so is ASI Air, that you strap onto your telescope, and then your iPhone or iPad tells that little computer what to do. Again, it's a beautiful thing that the ASI Air Plus just came out about 2 years ago. So it's brand new. Sky Fusion came out about 5-6 years ago, which really helped the amateur astrophotographers do their job. So basically, what they do is you tell them that you want the mount to point at a certain object in the sky. You want to take them the number of pictures, how long, and so on, and then it does it, and it keeps track of everything. Oh, wait a minute, let's go back here. So that's the capture software that's in those two computers. And then on your main computer, after you have your pictures taken, you can pull all those pictures out of your little computers, take them to your main computer, and the first thing you have to do is stack them. Because you have a bunch of either, like 3 minute, 2 minute, 1 minute, whatever you've been taking, exposures that you have to stack into one final picture. So Deep Sky Stacker is one of the free softwares that you can actually, don't even have to pay for, and it'll do a real good job. PixelSight is then what processes the pictures after you stack them. Oh, yeah, there's my observatory. That's where I was moving it. We used to live in Minton City when I was teaching at CBC, and we moved to Moses Lake here about 2 years ago. So I had to move my observatory. I had to take it apart and move it up here. All right, so what do we do in capturing images? Let's talk about that. Well, first thing we have to do is focus it. We have to get those, we usually pick out a nice bright star or a series of stars. Get focused on the stars. And I'll show you a little bit about that here in a second. And you have to be polar aligned. The telescope has to be pointed at Polaris, although Polaris is not true north. It's a few degrees off. So you start off by pointing to Polaris, and then you just move over a few degrees, and then you're pointing perfectly north. And your mount has to be right on in order to track the night sky accurately. Another thing that these little computers do is you tell it where you want it to point, and then you tell it that you want to center. Let's say we're going to go to the Orion. This is the Orion Nebula. We're going to go there. So you tell it you want to go there, so it swings over, points at it, it takes a picture, analyzes the picture, says, oh, it's not quite centered. It needs to be moved a little bit to the left. It moves the mount, takes another picture, looks at it again, goes, no, one more move. Move it again, takes another picture, and then it's centered. I used to spend hours doing that manually until they came up with these things to do that automatically. Within 30 seconds, you usually have it centered because it only needs to take about a 6 or 7 second exposure in order to see the stars and figure out where it's pointing. And then it stops once it's centered. Once you have that, like I said, you just tell it how many you want to take, how long, and you start the process. And in the morning, you have your pictures. All right, how do we focus? Well, one of the simplest ways is to get one of these are plastic backing off back masks. And you see how they have these slits and they're raised at different angles and so on. Well, those slits cause the stars to diffract. And that's on the next picture here. So you get these diffraction spikes from the star. And what you do is you turn your focus knob one way or the other until you get those lines, until you get this center spike to line up right down the middle. And when it does, you're in focus. But guess what? this little guy right here can do that too. You just tell it you want to focus. You pick out some stars that are bright enough, tell it to focus. In about 2 minutes, it'll focus it for you. Don't have to do that anymore either. I just talked about the framing. They just take the pictures and get it centered, and you're good. Now, why do we have specialized astronomy cameras? Well, they're a little bit different. They're actually more sensitive to light, and they have to be, because when we're taking pictures of the night sky, we're looking at things that are up to a few million light years away. They're a long ways away, right? Remember that? Here on the Earth, we have a great big star right there, our sun, that's flooding us with light all the time. Whenever the sun's up, right? Or whenever the sun's shining on our part of the globe. So our cell cameras and DSLR cameras don't have to be really specialized, because we got lots of photons coming from the sun to take really good pictures without really worrying about it. What we have to worry about with astronomy cameras is we have to overcome all the noise that can be picked up while we're taking those long exposures. So we have to increase the signal to noise ratio. And that's one of the reasons we have these specialized cameras for doing that. So what do I mean by noise? Well, noise comes in several forms. Just the heat from the camera itself creates noise. So one of the things that most of these cameras do now is they cool themselves. There's a fan built inside, and they actually can cool themselves up to 15 or 20 degrees below ambient temperature. And that helps decrease the noise. They're just the sensors themselves create some noise after you do long exposures. And one of the worst sources of noise is light pollution. Who's heard of light pollution? Most of you have by now, right? I don't even turn on my yard light. I'd like to go around the neighborhood and shoot out all the yard lights. They are just creating light pollution. They're not protecting anybody. In fact, if anything, you're turning on the light so people can see to steal from you better, as far as I'm concerned. It's kind of hard to fumble around in the dark and steal things. I don't turn on my lights at all outside unless there's somebody coming to my door that I know are coming, and I'll turn my light. And I don't. Light pollution has taken over the world. We were just discussing this before the show started, that there's kids out there right now, especially in some of the bigger cities, LA, New York, whatever, have never even seen the Milky Way, our own galaxy. Haven't seen the Big Dipper. They can't. It's wiped out. We're lucky here in Washington where we've got fairly dark skies, and we're right next door to Oregon. Oregon has some of the best dark skies in the United States, in the world. So you just travel a few hundred miles, get out there in the plateau of Oregon, and you got some dark skies. You can actually see things. So how do we overcome that? Well, we'll talk about that here in a second. I got some slides that talks about that. Yeah, cosmic rays can affect it. Just the sensor, the pixels in the sensor could have defects. It can cause problems too. All right, so reducing noise. Well, I talked about stacking. You take all those individual pictures and stack them, and you use these calibration frames, flats, darks, and bias. They are things you take beforehand that will subtract a lot of those problems. Flats, for instance, flats are, you take a flat, you shine a light into the telescope that's got a good pattern, nice pattern of light, and you take a fairly short exposure, and what it does is it picks up any vignetting, any darkness around the corners. It gets rid of dust shadows and other things that might happen between, the telescope and your camera, and you just subtract those. Darks, you take your camera, block any light from it, and you expose it for 1, 2, 3, 4, 5 minutes, however long your actual exposure is going to be, and then subtract those darks from it. those darks are basically eliminating any camera noise. And the last one, the bias, is kind of the same thing. It's sort of like the darks, but it also eliminates some of the other camera noise. By subtracting those calibration frames at the same time you're stacking, you get rid of most of the noise. Yeah, you do. Optimal exposure times mean the shortest exposure time you can do to get the best picture. Sometimes things are so distant, though, you might have to shoot 5-minute exposures. There's just no way around it, like distant galaxies. And then the dithering is a kind of strange thing. Dithering means, again, your little computer can tell between each frame, it'll tell the telescope to move about 10 pixels, like that, back and forth. And that gets rid of hot pixels that might show up in your picture. And then the software programs, we'll talk about more of that in a minute here. All right, narrowband filters are what's going to help us with light pollution. And they've done a really good job just in the last 5 or 6 years of producing some filters that eliminate most light pollution, which is great. I can take pictures sometimes with these filters with a full moon, looking right next to something next to the full moon, and it'll eliminate all that light. So what they do is the filters block everything except those narrow bands of hydrogen beta, O3, hydrogen alpha, and sulfur 2. Those are the primary bands of light that nebula and galaxies are emitting. So that's what we want that's the light that we want on our cameras. And by just selecting those bands of light, we can get some nice pictures despite light pollution. So monochrome cameras use these individually. It's a black and white camera basically, and you use the filters to get you color. The problem is you have to take a series of red, a series of blue, a series of green, and then a series of hydrogen alpha, beta, whatever. And it could take you 3 or 4 nights to get all the pictures together that you need. I chose the simpler route. Color cameras with one filter that has 2 or 3 narrow band types of light that it's letting through. And then you only have to shoot one series. And the color cameras are getting really good now. They're almost as good as the monochrome cameras as far as taking good pictures. All right, processing. Okay, we stack them. When we stack them, the picture's gonna look like this. That's what you can see. That's the Andromeda galaxy. That's the core of the galaxy right there. That's all you're gonna see. The reason being that the astronomy cameras save it in a linear format. It hasn't been stretched yet. We'll talk about it on the next slide here. So they're in a linear format. Everything, if you looked at a histogram, is just an example of what the light is doing. In the histogram, all the light is right here in that one little narrow section of that histogram. So the software, what it does is stretches that. Boom, there's the picture. Stretches that out into the final picture. DSLR cameras and your cell phone camera, they automatically do that within the camera. It just does it. Stretches it out so you see a picture on the way. Astronomy cameras, though, they save the image in a linear format, so you have to stretch it later on. Yeah, I talked about the Deep Sky Stacker. It's going to take all those individual pictures and stack them into one. And then the Pixins, I chose PixInsight. There are several software programs out there that will do this, including Photoshop. The problem with Photoshop is they want a lot of money. You used to be able to just buy it outright. Not anymore. Just like with everything else now, that you have to rent it, basically. You have to pay a monthly fee to use Photoshop. PixInsight, I like it because it's even better than Photoshop in some respects. One-time fee, and you get all of the updates free. So every month I get an update of new stuff. It's free. Okay, let's talk about how that works. So another thing that just came out in the last like 2 years, a guy has been working on eliminating noise and eliminating, well, basically allowing your pictures to be sharper. And he used AI. So what he did was he took all these software programs that that eliminate noise and sharpen your pictures. Instead of you having to tweak it, which a lot of people had to do for a long time, you had to take these software programs and tweak each one of your pictures, using it until it finally looked good. He took an AI program and showed it the software and said, okay, we want the picture to look like this. Do all the tweaking for me so that it looks the best it can, and then turn it loose. And within a day or two, he had a software that would do all of the tweaking that used to take hours, to do it by hand. So two of them are, one of them's called noise exterminator, one's called blur exterminator. All I have to do is say, okay, exterminate the noise. Within 30 seconds, boom, the noise is gone. See how noisy the pictures are up here? There's a lot of this background noise. And so you see all the green and blue and stuff in there? It's just eliminated immediately. And the stars are nice and sharp, round, like they're supposed to be. So the blurriness has been exterminated too. It's great, 2 pieces of software. How am I doing for time? Oh, just about, okay. Okay, so that's basically it. What I want to do is I'm going to run through some of my pictures, and if everybody's willing to stick around for a few minutes, I know I'm running over. Of course, we started a little bit late too. We started about 2 minutes late. Is I'm going to take one of my pictures and run through the processing. It should take about five minutes or so, but I'm going to run through some of my pictures first and just kind of show you what some of the things I've done with and what I've used as far as telescopes and stuff. So this is called the California Nebula. And as I pointed out here, this is one of those emission nebulas. So that's mostly hydrogen gas that's been ionized. It's been energized by the stars around it, so that it glows red. Now, here's an example of which telescope you might want to use. It's a fairly large nebula, so you want actually a smaller telescope. And then you're going to see that this 61 millimeter maybe is a lot because it can get those big nebula within the frame. If you go to a bigger telescope, it's going to zero in on a tighter, less of the night sky, so you won't get all of the nebula in the picture. So you may have to use a smaller telescope. All right, so 80 millimeter, the type of camera I used. ZWO has really been doing great stuff with cameras and telescopes and stuff. They're a Chinese company. They're doing a good job, and it's less expensive. 41 10-minute exposures. So that's what I took, stacked them, processed them, and got this picture. 1,000 light years away. There's the Trifid again. I used it at the very beginning. The Trifid and Lagoon Nebula are fairly close together, and they're both star-forming areas. Anytime you see a lot of hydrogen gas and bright stars in the area, you know that hydrogen gas is being turned into stars. So astronomers study these areas a lot. Lagoon Nebula is a good one. The Orion Nebula is another good one because they're fairly close to the Earth. They're only 5,000 light years away. That's pretty close, really, in astronomical terms. So they look at these places to study how stars are formed. Here's one I really like this one. This is called the Heart Nebula. And the first time I took pictures of this one with that camera, and it was before I had the blur exterminator and the noise exterminator, and you can see that there's another one called star exterminator. I went back, I'd taken it like 4 or 5 years ago. I went back and reprocessed it with those new exterminator softwares, and it just made it go pow, just popped right out. It's just awesome. So I went back and reprocessed a whole bunch of my pictures. And that's kind of the way things go. As things as things get invented, you can do more things, get better pictures. This is the rosette, again with the 80 millimeter because it's a fairly large nebula. Again, a star forming area. See all those stars in the middle? A lot of those have just been formed from this hydrogen gas condensing down and forming new stars. This is one of my favorites. And I used that telescope, 61 millimeter, because it's big. It covers, I'd have to look it up, but it covers several light years, a bunch of light years, probably a couple of hundred light years in range. I think it's 4 full moons across. So I had to use a smaller telescope to get the entire nebula. Supernova remnant, which means that it's from a supernova explosion of a star that occurred about 8,000 years ago. And we know this because Chinese astronomers saw it. It was so bright, you could see it during the daytime when it exploded. And that's the gas that's left over, still expanding. North America Nebula. What looks like North America here. Pelican Nebula. Pelican Nebula right there. Can I see that? Sometimes they're kind of hard to see, but they come up with names. Now, all of these have a catalog number 2. I just didn't put them up here. But both of these have NGC numbers and probably an IC number too. So they're cataloged within those catalogs with NGC numbers and IC numbers. I just use the common names just to kind of keep it simple. Eagle and Omega, again, star forming areas. The Eagle Nebula is famous because probably the most famous picture that the Hubble telescope took was of that central portion. You see that? You see that dark portion right there in the middle? Kind of looks like a, I don't know, it sort of looks like a flying horse to me or something, but that's the pillars of creation that the Hubble telescope took a picture of. It, much larger, and it's in the Hubble palette too. What's called the Hubble palette, which means it's in greens and blues. And that's kind of another neat thing. We can manipulate the colors to bring out more detail. We don't have to have red, for instance. We can change them to blues and greens and you get more detail sometimes. Another one of my favorites. The Flaming Nebula, and the Horsehead. Now, since that's dark, that's what kind of a nebula. A dark nebula or absorption nebula, because it's blocking the light, absorbing the light, and that's where that horsehead shape comes from, is by blocking that light. Same thing with the flame nebula. That dark area is the dark nebula. The rest of it's hydrogen gas. One of the reasons I like this one is because this star right here is part of Orion's belt, the Orion constellation. So on the next slide, there's Orion's belt. Those 3 stars at the top, and there's the Horsehead and Flame right next to that. Down here is Orion's sword. The middle star of Orion's sword is not actually a star. It's a nebula, the Orion Nebula. You just can't see it with your naked eye. You have to take a picture of it in order to bring out those colors. Okay, let's go back to the eyes for a second. Just an interesting thing about this. One of the main reasons you cannot see these nebula with the naked eye is they're not bright enough. Remember those cones and rods I was talking about? Rods turn on with just very little light. So in a darkened room, you can still see because the rods are working. They have enough light to work with. But you don't see color. You see just rays. You have to have more light to see the colors. Well, these nebula don't give off enough light to turn on our cones, so we don't see color. You have to take a picture. Orion and Ring Man Nebula. Easy one to take. This is one of those, it's kind of like the moon. It's so bright, you only have to take 30-second exposures. In fact, I think, yeah, 1 minute, 180 1-minute exposures instead of doing 45 5-minute exposures, whatever. So I just took a whole bunch of 1-minute exposures. And the beauty of that is, by doing that, you're going to get less star trailing, you're going to get less noise by going with less exposure. 1-minute exposures are great. This is awesome. That's called the eye of God too. just kind of a common name. It's called a planetary nebula because it's round. When astronomers first started seeing these things, they weren't sure what they were. It's called a planetary nebula. There were a nebula that are round. You see that white dot in the middle? That's a white dwarf. It's the remnant of the star that exploded and produced, well, it didn't really explode. It just shed all of its outer gases. It wasn't a true explosion. And produced that colorful nebula around it. That's what's going to happen to our sun in about 3 or 4 billion years. It's going to start going through this phase. It's going to turn into a red giant, which is what this one did too initially. It turned into a red giant. The red giant's going to expand. That's what's going to happen to our sun. And it's probably going to expand out to probably almost to Mars orbit. So you can imagine what's going to happen to the Earth. Everything ends. Everything has an ending, even the Earth, and even our sun, unfortunately, right? So it's going to expand to a red giant, and then right after that, well, not right after, it's going to be probably a few million years, it's going to condense down into a white dwarf. Well, it's going to start condensing down into almost a white dwarf, then it expands real quick and throws off all those gases, and then leaves that white dwarf behind. So that's a typical planetary nebula. Okay, I'm going to move right along now. This is a jellyfish nebula. So again, the 80 millimeter telescope, wide range. Bubble nebula. That bubble in the middle is created by gases being pushed away by the very hot star in the middle, creating a bubble shape of the gases. There's a Heart Nebula again with the neighboring nebula called the Sol Nebula. Again with my wide angle 61 millimeter telescope. Elephant Trunk Nebula kind of looks like an elephant with a trunk. It's in the middle of a huge nebula region with lots of hydrogen gas in it. Same thing with the Cocoon. The Cocoon Nebula is kind of neat because you see all the dark areas, kind of grayish and brown. That's all dust. It's dust. Same thing with the Crescent Nebula here. Lots of dust in there, along with the hydrogen gas. Okay, this is back to another type of nebula we talked about at the very beginning. It's got that bluish green color, so it's a reflection nebula. That's got a lot of dust there that's reflecting the light from those center stars. So the stars in the very middle of that nebula, the dust around it is reflecting it out into a bluish tint to it. And you can see all the dust out here, lots of dust black down there. Okay, back to our horse head and flame a little bit closer. All right, here we are with Andromeda Galaxy, and I mentioned the other two galaxies before, M110 and M32. Oh, by the way, Milky Way and Andromeda are moving towards each other. They're going to collide in another 2 or 3 billion years and merge into a huge galaxy. That's kind of what's happening with this one. There's two galaxies there. There's a galaxy over here, and there's another one over here. Together they're called whirlpool galaxy. The big one is sucking material off of the littler one. That's why you see that band of light going over to the bigger galaxy. The gravity from the bigger galaxy is drawing material off the smaller one. Yeah. Now you see what we're looking at here too. 23 million light years away. Now we're looking back. The other thing about this is a telescope is a time machine. That's what that galaxy looked like 23 million years ago when that light first left the galaxy and then landed through my telescope onto my camera. So you're looking back in time 23 million years. Same thing with this. Now you're looking back 8 million years, 30 million years. And these are a pair of galaxies right next to each other, 12 million light years away. And I've got some close-ups of the two of them, and I'll just show those here in the next slide here. So this is the cigar in Messier 82. So Messier catalog that one. This is interesting because you see all that hydrogen gas coming off of it? Really active galaxy. It's exploding with star growth. And that explosion of star growth is causing all that hydrogen gas to be pushed out of the galaxy. And its neighbor, M81, Bode's galaxy, they're real popular to take pictures of because they look so cool. Another one looks real cool, Pinwheel Galaxy. And now we're looking at, I had a 10-inch truss tube reflector telescope for a while. I was having some issues with it, so I sold it, but it does some really good jobs on these galaxies. And that's what I use for this one and this one too. So it's a fairly large mirror, 10-inch. Same thing there. That's a triangular galaxy. Fairly close, kind of in the range of the Andromeda galaxy. The last few here, okay, look here, 60 million light years away. This is what's called the Hickson 44 group of galaxies. There's a lot of galaxies in these pictures. There's the elliptical one there, there's a spiral, the regular spiral with the edge on, and a couple of other ellipticals. Even more here. Some of these are awesome because most of those things in there are galaxies, just at different distances. That's why I didn't put a distance on there because they're all at different distances. This is a fairly popular one. 3 galaxies together in a group called a Leo triplet. Okay, so there are things we can see these globular clusters are right around our galaxy. There's about 200 of them at different distances. These are all fairly old stars. Probably were around even before our solar system was formed. So they're fairly old stars, and just a cluster of stars. We don't know if there's any planets there or not. It's hard to tell. All right, some of the things I've taken closer by, like I said, moon is fairly easy. And they use just a Canon camera to take pictures of the moon and the sun. So this was just recent. Right now, the sun is in very active period. About every 11 years, it cycles in and out of being inactive or active. What I mean by active is there's a lot of sunspots, solar flares, prominences, things like that going on. And whenever there's a big solar flare, sometimes you might get what's called a mass ejection event, where a whole bunch of particles are ejected out of the sun and start traveling out into space. And if they're aimed at the Earth, we could have problems, primarily with our electrical grid, our cell phones, and things like that. If we don't start shutting things down when that happens, we could be burned out and probably take years to recover. So we have to kind of keep an eye on when the sun's active to make sure we don't get hit with that. We've actually been hit a couple of times before we had all of this electrical grid system. Right after the telegraphs were invented, and I think it was during the Civil War, in fact, we got hit with one of those mass ejections, and it burned out a whole bunch of telegraph wires. So we don't want to have that happen again. 2012, 5th of June, Venus transited the sun. It's the last time that's going to happen for over 100 years. So I had to get a picture. then when it happens again, I think it's about either 7 or 8 years later, it's going to happen again. So it happens in 2 times fairly close, and then it's 100 years before it happens again. In other words, the sun or the Venus went between the sun and the Earth where we could see it. Same thing with Mercury here. Mercury does a little more often. This is back in 2016. Mercury's that little dot down there. The sun. Anybody get down to Oregon, see the eclipse 2017? We did. We couldn't miss that. We were scheduled to go down to Texas to see the one that just happened a few weeks ago. And I kept watching the weather. I reserved a campsite a year ahead of time in Fredericksburg. And then rain and clouds started moving in, and Fredericksburg was going to be clouded out, so we canceled. we didn't want to go through the hassle trying to find a spot somewhere else because we knew there was going to be so many people trying to do the same thing. We just canceled. But it's awesome to see it. If you ever get a chance to see a total eclipse, there's partial and there's total. They're not comparable. You're either in total or you're not. As simple as that. Because we were in partial here, which I'll show you here in a second. So here's a composite of the eclipse as it made first contact over there on the right, all the way through the tower, and as it moved off. Yeah, this took me a while to get. Anybody know what that is? What does it look like? It's the International Space Station in front of the sun. I used to have a software program that he actually stopped doing it because he was losing money on it. But this guy was putting out on the internet when and where you could go see things like the space station in front of the moon or the sun and things like that. And so I kept an eye on that, and I noticed that there was one coming up that was right outside Benton City. So I went out there, set up my telescope, and I used my Canon camera and turned it on video. I started about a minute before it was supposed to happen and let it keep running until 2 or 3 minutes after it was supposed to happen. And then when I looked at the video, 3 frames had the space station in front of the sun out of that video. That's the only way you can do it. You can't just try to snap it. The more it goes past too fast. So you can't do that. You got to shoot video. More sunspot activity. Lots going on right now. Yeah, same thing with the moon. The easiest way to take pictures of the moon is to use the Canon camera again, shoot video, and then there's another software program that you stack. You take the best frames out of that video and stack the best frames, and you get a really nice sharp picture. Like that one. That's a nice one there. Lunar eclipse, they happen quite often, but it's nice to see one because they're pretty neat. You watch the shadow. It's a shadow of the Earth going across the surface of the moon. And when you're in totality, it typically turns the moon orange. Here's what we saw in Moses Lake on the April 8th. That's as far as the moon got for us, is right there. Okay. There's my 2 websites. There's the Veil Nebula again. Let me ask you before I just jump right into it, is anybody interested in seeing how I process any of the pictures? If you're not, I'll just stop now. If I've already burned you out. You want to see it? Okay. All right, just give me a second. Get out of here. All right, so here we are. Deep Sky Stacker has already stacked the pictures, and there they are. That's what you get. That's the final image from Deep Sky Stacker. Looks like pea soup or something, huh? So what you have to do, and what I've done, in fact, let me just show you this real quick. There's what it looks like before it's stretched at all. As I said before, it's all linear right now, so all you're going to see is a few stars. The first couple of times I did that, I was going, boy, what happened? I didn't get anything. But then, so then this is PixInsight. This is the software PixInsight that we're looking at. And what I do when I do this right here, I click on this little nuclear thing right here like that, and you see what happened. It now has temporarily stretched the image. So you're seeing the color and everything that's in the image. But it has to be, there's some things that has to be done to get rid of basically all of the light pollution and other things that are showing up here now. I'm going to skip the cropping thing. I'm going to go right to what's called dynamic background extraction. The dynamic background extraction is going to do the first step of basically getting that color to look right. So what it has done now, you see all those little squares around the edge. Those squares are looking at the image around the actual nebula. The center of that is actually the Rosette Nebula. You just can't see it yet. So what it's doing is looking at the background and saying, whoa, that background is a mess. Let's straighten that out. So what you do, and this is one of those what's already been kind of set up, I just have to say, okay, fix it. It's working. Okay, there it is. It's partially done now. I'm going to close that. What it did was just divided out a whole bunch of that color that was a mess. Now I actually have to re-stretch this to see what happened. There we are. There's a rosette. And that's just the start. And then there's a color correction. The color's not quite right yet, so you do this. You zoom in on this thing. Oh, let's see. I don't have my mouse. I can't. Okay, I'm not even going to zoom in on it. Let's do it this way. I'm going to make a little square here of the sky. It's preview. And then I'm going to look at the colors here. Let's see what's about. Okay, so, and now I'm looking at these numbers down here to see how bright it is. And I'm going to basically double that and then put that in my little, I'm going to pull up the target image. So I'm going to put the preview in there as my target image. Oops. This mouse is really sensitive. So, okay. I'm going to change this to, oh yeah, that's right. Let's go 110. And I'm not able to use my real mouse up here, so this is going to be a problem. There we go. Oops. Let's do it this way. Yeah, that'll do. Okay. And we're going to apply that. Okay, it's going to adjust the color a little bit. Probably won't see too much of a difference. Oh yeah, you got a little bit of a difference. Now let's get rid of that preview. Delete. Okay. Now we're gonna do this again. There goes, and re-stretch. Okay. Now comes the real magic. We're going to do the noise. Remember the noise exterminator, blur exterminator I was talking about a minute ago? Now we're going to, well, let's see. Let's do this first. Get this thing. I need my mouse. Yeah, we'll just do it this way. Okay, I know I can do it. Okay, it's going to take a couple minutes. And in the background, there's still a bunch of noise that's going to be eliminated here in a second once it's done. And it's starting. It's parking. Almost done. Okay, now let's see if I can zoom in on this. I can't. That's pretty cool. Well, it's zoomed in, but that's too much zoomed in. Well, let's do that. Okay, you see, we're looking at the stars really zoomed in on those squares. You see that? You see how nice and clear that is? Okay, I'm going to go back out here, and I'm going to back out of the. I'm going to undo the noise exterminator. Okay. Oops. Wow, it went too far back. Wow, it went back before I even did the. That's great. So I'll have to restretch it, I guess. Of course, nothing's going to look like it's supposed to now. Yeah, now you can see it. See what you see in there now? See all that red and green and purple stuff? That's the noise. Okay. And by getting rid of that, which I'm going to do right now with just this, redo the color calibration. What happened was when I hit it, it redid everything. It backed me up 2 steps instead of just 1. Okay. Now let's do this. Stretch. Okay, now let's look at this. All right. It's still not completely cleared out. Let's see. Okay. But you see how it's not as red and green and blue. Most of the noise is gone now. Oh, and you can see some of that aberration I was talking about too on the stars. Let me see. Star right here. See the orange and see the orange blue? That's some of the things that will be eliminated with the next step, which is blur exterminator. So you do this. And I'll stop after this step because I know everybody's getting tired and late. But I'll kind of explain the next couple of steps just so you know what will be done next. It takes me about, probably if I'm taking my time, about an hour. It used to take me 4 or 5 hours without these AI, because what this blur exterminator and noise exterminator did was take away all that tweaking that you would have to do. You'd have to, okay, let me try these settings, do it. Oh no, that doesn't look right. Okay, redo the settings, do it. Oh, that still doesn't look right. Back and forth till you get it right. But with the blur exterminator and the noise exterminator already set, already tweaked, you don't have to do that anymore. It does take a couple minutes for it to do it, but it's a whole lot better than doing 2 or 3 hours of tweaking. Does anybody have any questions while we're waiting for that to finish up?
Well, first of all, great presentation and excellent job on your photography. I've been to a bunch of these, like Seattle, Columbia Basin College. Really.
Oh, thank you.
So that's that. I'm just curious, what kind of mount do you have there?
This is a ZWO AM5 mount.
All right.
Yeah, it's fairly new too. We probably came out with about 3 years ago.
And then subtracting, like you're doing with the darks up there, the fact that you're at old Canada, all this, what kind of a what kind of a chore is it to pull? I assume you can pull the line that somehow could drift or some other way.
Again, these mounts just get so new nowadays. Basically, I know the north is about right there. So basically, you just take the mount, point the telescope basically to the North Star, and then you can tell the mount that you're going to over a line. The mount's going to move the telescope about 60 degrees over here to the side. Take a picture. Then it's going to analyze the picture, and it's going to tell you, okay, you can decrease a little bit. You can move it up 2 or 3. Well, it'll tell you the maximum amount to move it up or left or right. You move it, well, it'll tell you how to move it. You take another picture, analyze again, okay, you need to move it this way and up a little bit more. And it'll tell you the amount. You go by, look at the amount, how much you tweak it, you can move these knobs back and forth, you move the amount of voltage, and telescope up and down. Yeah,
So it's kind of like an automated drift alignment.
yeah, almost a lot easier. Once you get good at it, within a minute, you can have that full alignment.
Really?
Yeah. And the mount that I have in my observatory, the beauty of having an observatory is once it's full alignment, you really touch the moon.
And is that the same model?
No, that was a Paramount NYT mount.
Oh, Paramount?
Yeah. That was, what is this? ZWO, AM5.
Because I've got a Mach 1 and
Okay.
it's just a chore.
Yeah.
I mean, it's a beast and it's a chore.
And
And that's
this
less a squeeze up you.
is not an expensive either. It's like $1,500 to $2,000.
Right? Yeah. You know what else I like about this is you can, let's say, what kind of speed you can,
Yeah, it's got its own bearing base and stuff.
how much weight will that carry?
It carries, well, what can you see on this mount? What don't you see on this mount?
Pardon?
What's missing on this mount? You see all the mounts, you don't see something on this mount. It's missing.
Oh, I don't see power rates.
Yeah, there's no power rate. It's a different kind of mount. It's called a,
See, I thought maybe you just didn't bring them because you've got this small scope and you're just here.
No.
You just
that's an easy one. Until you get up to about, I think, 20, 25 pounds. Let's get up to about 20 pounds. Once you get to about 25 pounds, you have to power rate. But you really want to go.
20 pounds would be all wrapped up. That would be what, like a 90?
Yeah, I don't know. It depends on what else you put on you, because you start putting on, you know, of course, the beauty of this too is the guide scope and the ASI air and focus are so damn good.
I don't think it's bothering me.
Anybody else have any questions? Because you could like this.
What would be a good beginning?
Yeah, that's a really good question. Well, I started last March, and I would start with probably like the least expensive ways is like a 6-inch, probably 6 inches less strong, but still years. Because they're 4 inches. Yeah, they got 3 or 4 inches. Some of them are cable mounted, and they have the mount and the telescope. They're like 4 inch telescope. You know, and you on the Regina Astro cares everything. In fact, what you should do is call Regina Astro and say, okay, here's what I'm gonna do, and they'll tell you exactly. They're probably the premier astrophotographer in the school, and they took over from OPT left, I don't know what happened to them, but I love them, so now I see them. Cool. Regina Astro is a lot.
Where's Gino last?
They're in California, so was OPT.
Or this side? So what do you do when it's bad weather, worrying about, like, because it's kind of just thinking.
Oh,
like,
that's
what
why
if-
I did your
What if you wake up and it's raining outside?
Oh, I make sure that that's, I check weather breaker.
Yeah, but I mean, it happened, I mean, that, you never got a spot, you never.
That's why I'm not sure, my front, also, not in good, I have to roll away the roof. So it's protected all the time, until I want to do something, roll the roof back. Yeah, when you check the weather, it's gonna be bad weather. Sometimes when I walk them, if I know it's gonna be good weather, I'll start to think, this thing is beautiful because it's so mobile. Just pick up there, wherever you want. So I pick it up, back door, and set it in the back door, and get it full line real quick. It's 20 minutes.
Is the other one in your observatory more, permanent?
Yeah, it's got a concrete pillar. It's got steel mount, steel corner above that. You get behind it, get above the wall.
And you have a thing that opens up or something?
Yeah, it's rollaway roof. It has roofs, it's on rollers. You can stick the roof back.
Oh,
I have to be in a picture, you know it? The first picture of the observatory when I'm filming it, it has 4x4 posts that has rails on it. And the roof rolls off on those rails and it's,
so how will you use that telescope when you move your observatory?
I had to start all over. I had 400 pillars, and then I took like steel pillars, put them back, these bolts coming out of the concrete, and put my steel pillars, bolt them back on. And I had to, but I had a good neighbor too. I just took the walls off the observatory, took the floors apart, took the roof apart, and he had a trailer that I put everything on. And ended up in the walls lake and nothing on things up and rebuilt the wall, all I did was put the walls back up. And squared. I always poured the pillars. I had to buy a observatory up before the house was started. The foundation was being poured while I was rebuilding my observatory and whatnot.
It is still like this one.
Yeah, this is really nice.
Even though it's a lot smaller.
It's easy to control, it's easy to transport, it's easy to clean out, some of those old. Nice, so. I try to keep up. I'm really puzzled, it's fun.
Do you like it? Do you like it?
Oh, yeah. I think I've learned a lot too.
You know, yeah.
Keeps them busy.
It's the best way to retire, is that's something you do. You have a question?
Yeah, so the sky fusion, is that part of, does that come with this mount setup or?
This is actually the ASI air, the Sky Fusion on my big mount. The Sky Fusion comes from Paramount too, from software bit. Software bits makes the Paramount mount,
Right,
and it also produces the Sky Fusion box, which you figure out.
which you have right there.
No, this is the ASI air.
Oh, that's,
This is
the
the-
sky fusion on it.
No, the Sky Fusion is on my other.
Oh, okay, that's the inside here.
Yeah, they've got the same color pop, but it's black and red.
Right. So that inside fusion, that is part of, that's just part of your mouth.
Yeah, it comes off. This is, like, everything comes off. They're all plugged together.
Nice.
So it's called the ASI Air Plus. It's part of, CWO has Everything that's on here basically was made by ZWO except the telescope. Telescope was made by ATP. Yes.
I have last question. So after you do this, thing that you just did with the picture.
Right.
what's the next step?
Oh, yeah, I didn't do the other steps, but okay, well, right after that, I do the star exterminator. The star exterminator takes all the stars out of the picture and makes it a separate picture. So the nebula now is all by itself. Then what you do is you take, let me go back here and just get rid of this for a second. Yeah, get rid of this. Okay, that's okay. Oops. So what you're going to do then, oh, and I already eliminated, oh, darn it. I messed up. I eliminated, I got rid of I closed this and I shouldn't have, which means I don't think I can do it now. Let me see if I can. I'll go away. I hate not having my mouse. Yeah, I can't.
Mike, have you ever thought about, maybe offering a class or something?
I have. I've done a couple classes at CDC with people. Yeah, I'll talk to her. We can arrange something. What's that?
You said talk to her to get you here?
No, just to arrange. I'll do it.
Yeah, Mike's an old kid.
But anyway, basically, up here, you see the screen transfer function, all that does is temporarily stretch the picture. Well, once I close it out, now this is permanent. I can't go back. So it's kind of at least I haven't done it, but I didn't notice I did it. But what I was going to do was take it back, and then what the next step would be the permanent stretch, and that's the histogram transfer function. That will permanently stretch, and what you want to do is you do the star exterminator first, separate the stars, and leave it to the side, and then you permanently stretch the nebula to where you get all the colors to come out. And then it looks like, and then you can process the stars separately, get them to look just the way you want to. And then you can do this thing down here called pixel math. And it's just like it says, it's a math processing thing. So you're going to add those two pictures back together. You're going to put the star picture and the nebula picture, and then put a plus sign between the two of them, and boom, and merge the two pictures back together again after you've processed them separately. What that does is allows you to process the nebula just the way you want it, and process stars the way you want it. Because when you try to process them together at the same time, sometimes you get a mess. The stars don't look right, or the nebula doesn't look right. So by processing them separately, boy, it saves a lot of headache later on. And pixel math then just puts them back together, and then you come up with a picture like this.
Michael has his, art in the museum, right now, but he will have his photographs on the 31st. And he's already sitting there now, if you are interested.
Yeah, there's the picture when it's done. And that one's fairly recent. I just took that one with that new big telescope, the 140 millimeter one.
You in Moses Lake or outside of Moses Lake, or where's your laboratory?
What's that?
Where's your laboratory? Is it, are you using the city or you out? Okay. Fairly full, rural.
Yeah, it's an apartment, a lot of dead end road. But if I have to go, we jump on it, yeah, it's kind of nice to study a little bit like this. There's one house that's like probably a quarter of a mile away, and they had bright lights every foot all the way around the house. It looks like a spotlight shining on, a quarter of a mile away. You know, Astro, and they had all of the GWO products. Astromark is the top of the website really buy these and sell these. There's a fee, it's like, it's not very much, it's like $5. Astromark.